and good morning. I am Professor Devendra Singh, taking the course on machine design, and this is our 10th lecture. We will start design against dynamic load in this lecture. अभी कुछ जो नो लेक्चर में हमने डिज़ाइन कॉन्सेप्ट्स अगेंस्ट स्टैटिक लोड देखे हैं, थ्योरीज ऑफ फेलियर्स वी वर studying in last lectures, and we have covered the theory of failure, that is maximum principal stress theory, maximum strain theory, maximum shear stress theory, maximum strain energy theory and distortion energy theory. We have also discussed the graphical representation and which theory should be used for what type of materials and what type of condition, which theory should not be used. ये सब चीज़ें हम डिस्कस कर चुके हैं. थोड़ा सा पार्ट बचा है जो डिज़ाइन अगेंस्ट स्टैटिक लोड में बचा है, वो है ग्राफिकल रिप्रेजेंटेशन ऑफ मैक्सिमम डिस्टॉर्शन एनर्जी थ्योरी. एक्सप्रेशन लास्ट लेक्चर में वी हैव एस्टेब्लिश्ड, सो उसको थोड़ा कवर करेंगे इसमें और फिर बात करेंगे डिज़ाइन अगेंस्ट डायनेमिक लोड कॉन्सेप्ट्स के बारे में स्टार्ट करेंगे इस लेक्चर में. सो आज इस लेक्चर के जो कंटेंट्स हैं वो कुछ इस तरीके से हैं. फर्स्ट वी विल discuss the graphical representation of maximum distortion energy theory. Then we will discuss what is the dynamic load. Dynamic load क्या होता है, कि कैसे उसे बताते हैं, क्या क्या समझते हैं कौन सा डायनेमिक लोड है. डायनेमिक लोड की वजह से जो स्ट्रेसेस हैं वो किस तरीके की स्ट्रेसेस होती हैं वो डिस्कस करेंगे. एंड देन वी विल डिस्कस अबाउट एम्पलीट्यूड स्ट्रेस, मीन स्ट्रेस, स्ट्रेस रेंज, and finally we will try to cover the determination of the endurance limit, because in static design we were considering the failure stress for our ductile material is the yield point in tension, and for brittle material the ultimate point in tension, the ultimate tensile strength. Against dynamic load we consider a new strength, that is called endurance limit or fatigue limit or fatigue strength. If these are also having some meaning, we will discuss when we will discuss about the dynamic design or design against dynamic load. So, the graphical representation of von Mises theory or the maximum distortion energy theory expression, this is sigma 1 sigma 2 plane, O is the origin, and the expression for biaxial state of stress, this is the expression for factor of safety 1, and this is the equation of ellipse. So, where this equation of where this ellipse intersect the sigma 1 axis and sigma 2 axis, we just put sigma 1 is equals to 0 and sigma 2 is equals to 0 in this equation. We can find out the point where it will intersect. So, if we want to get the points where on the sigma 1 axis where this ellipse intersect, ये ellipse sigma 1 axis पे कहाँ कहाँ intersect करेगा उसको अगर हमें determine करना है, उस point के coordinates determine करना है. So, we just put the ordinate value 0, that is sigma 2 is equals to 0. So, we will find what is sigma 1. So, sigma 1 is equals to plus minus s y t. As you put sigma 2 is equals to 0, it will become equal to 0. Sigma 2 is equals to 0. Sigma 1 is square should be less than equal to s y t square. So, sigma 1 is plus minus s y t. So, the coordinates is this is s y t and 0. 0 मैंने यहाँ पे लिखा नहीं है. So, it intersect at s y t, that it yield point in tension. Then on negative side, this is minus s y t. Assuming the material I am discussing with for which is having the same value of yield point in tension, yield point in compression, having the same magnitude, that is why just replace this with negative sign. If it is a different value, then the case will be different and handled will be differently. Then if we want to get the points on sigma 2 axis, then we will put sigma 1 is equals to 0 in here in this equation, and we will get what is sigma 2. It will be again plus minus s y t. This is very simple. So, this ellipse will pass through these 4 points. So, if you draw sigma 1 minus plus sigma 2 square plus, and this minus is not there, then this is the ellipse which is passing through these points, and this is the safe zone. This is green zone is the safe zone with factor of safety 1, and the boundary of this ellipse, ये जो boundary है ये failure points हैं. Then this is sigma 1 and sigma 2, these are two planes which are principal planes. Then line or a plane, this is another plane which is having an angle of 45 degree with sigma 1 and sigma 2. So, this is nothing, this is a shear plane. So, this line we will call this is a shear diagonal, and as it is having this angle and this angle, this is theta is 45 degree. So, the equation is sigma 2 upon sigma 1 is equals to minus 1, right, because the angle we are measuring either this is minus 45 or this is 135. So, this is the equation of this line, and this is called shear diagonal, where shear diagonal intersect the boundary of this ellipse. It will determine this point will determine the shear stress or shear strength in the yield point. And if we solve this equation, this and this equation, then we will find the coordinates is 0.577. The coordinates are 0.577 SYT and 0.577 SYT. This is shear plane. So, we can say according to the maximum distortion theory, the shear stress at the yield point will be the maximum value, that is 0.577 times of SYT, and similarly we can determine by the maximum shear stress theory. So, this is safe zone, and this was the yield point shear stress according to maximum distortion in theory. हमें हमेशा ये याद रखना है 57.7% ऑफ SYT मैक्सिमम डिस्टॉर्शन एनर्जी थ्योरी के तहत है और 50% SYT का मैक्सिमम shear stress थ्योरी के तहत tau by T. Tau by T is the shear stress at yield point. Now, if we include some factor of safety, so we will use SYT upon FOS on the right hand side, and the equation will become this is only the change. Now, the only points where it intersect, so sigma 1 sigma 2 की वैल्यू जो होगी सिग्मा 1 एक्सेस पे वो प्लस माइनस SYT अपॉन FOS होगी और सिग्मा 2 के ऊपर प्लस माइनस SYT FOS होगी. जैसे पहले हमने ड्रॉ किया था वैसे ही हमने ये पॉइंट्स निकाल लिए हैं, ये पॉइंट्स लोकेट किए, ये पॉइंट्स सिग्मा 2 एक्सेस पे. अब ये भी एक इक्वेशन है जो इलिप्स की इक्वेशन है, इस इलिप्स को हमने ड्रॉ किया. दिस इज द इलिप्स with factor of safety, with the desired factor of safety. Now, this is again sigma 1 sigma 2 are the principal planes. So, this line it represents the shear diagonal, and the equation of shear diagonal is this. If we solve this and this, we will get some value of this point. Now, this point is 0.577 times of SYT upon FOS, because factor of safety we have included. So, this is there. Right. Now, this bigger one is the ellipse represented for factor of safety 1. This is the equation, and now if we have incorporated some factor of safety. So, this red zone, this zone will be considered as the danger zone for factor of safety 1, and the safe zone for factor of safety is the greener zone. This is safe zone. Now, if we want to compare various theories of failure, so again sigma 1, sigma 2, these are the two planes, these are the points SYT with factor of safety 1. This is the representation of maximum principal stress theory we have discussed in the last lecture. Now, this is our maximum shear stress theory. Now, this is our maximum distortion energy theory. So, this is shear diagonal. So, according to maximum principal stress theory, the shear is tau y t is equals to SYT. This point is 57.7% of SYT, and this point is 50% of SYT. Here, this is, if we consider opposite nature of stresses, this is the unsafe zone according to maximum distortion energy theory and maximum shear stress theory. So, this and maximum principal stress theory says this is a safer zone. So, whenever material is subjected to the opposite nature of stresses, then we do not use maximum principal stress theory, and in case of the, even in case of the brittle material also. Now, this is our ellipses maximum distortion energy theory. So, maximum shear stress theory in तीनों में, that is the most appropriate theory and will give the most conservative or most safe design, and it gives the result directly. So, we always use the maximum shear stress theory for this for the design of the component made of ductile materials, and maximum principal stress theory principal stress theory for the brittle materials, but we should always consider the what type of the stress is subjected to the material. It should not be opposite in nature. So, this is all about the theories of failure that I have discussed. Now, design against static load is over, and the next topic we are going to start, that is design against dynamic load. So, first of all, what is dynamic load? Load or force which either vary, change in the magnitude or change in the direction with respect to time is called the dynamic load. So, here the magnitude is varying with respect to time. So, this is a dynamic load. It may be like this, it is tensile, it is negative. So, it may be like this, it may be like this. So, this is also a dynamic load. It is changing the magnitude as well as the direction or the nature. For some time it is tensile in nature, for some period it is compressive in nature on the negative side, then again it will go to the tensile in nature. So, this is a dynamic type of loading. So, we in mechanical engineering, most of the elements are moving. So, the load actually comes on the mechanical components always of dynamic in nature. So, we should learn the design concepts against dynamic load very seriously, and due to this dynamic load, what kind of the stresses induced in the material. For design purpose, we will discuss. There are number of types of the stresses you can think of, but there are three in my opinion which I should discuss. मेरे हिसाब से ये तीन स्ट्रेसेस हैं जो मुझे यहाँ डिस्कस करनी चाहिए, एंड इट विल कवर the concept related to design against dynamic load. So, first one is completely reversible stress. First one is the completely reversible stress. Stress is what? That is load upon area. That is quantitative definition of the stress. Stress in fact is the resistance offered by the material against the deforming load, externally applied deforming load. So, if we are discussing about the completely reversible stress, so the stress should induce with same magnitude in tension as well as in compression. So, the best possible example for this is the bending. with torsion. Rotating shaft is the best example. If rotating shaft is subjected to some transverse load, एक shaft है rotate कर रही है, उस पर transverse load है, इस शाफ्ट को अगर मैं बात करूं, ये रोटेट कर रही है, इसका एक फाइबर है ए बी, दूसरा फाइबर है सी डी, तो हाफ रोटेशन में अब ये इसका ट्रांसवर्स लोड डब्ल्यू है, हाफ रोटेशन के लिए ए बी कंप्रेशन में होगा और अगले हाफ रोटेशन में सी डी कंप्रेशन में होगा और ए बी टेंशन में आ जाएगा, यानी कि सेम फाइबर इज सब्जेक्टेड टू द सेम मैग्नीट्यूड of stresses of opposite in nature, that is called the completely reversible stress. And completely reversible stress is the most dangerous state of stress. आप किसी तार को अगर तोड़ना चाहते हैं बिना किसी टूल के, इफ़ यू कैन बैंड दैट वायर, वो सरिये को अगर आप मोड़ लें एक बार इस डायरेक्शन में और उतना ही अपोजिट डायरेक्शन में, यू कैन ब्रेक इन टू पीसेस without using any tool. So, what you have induced in that wire or that rod, that is the completely reversible stress. आपने same fiber को same magnitude tension and compression दी, that is called completely reversible stress. So, अगर हम completely reversible stress की बात करें, उसे draw करने की बात करें, so completely reversible stress draw करेंगे तो same magnitude जो हमारा load है इसमें उतना ही ऊपर की तरफ गया और उतना ही नीचे की तरफ गया, ये टाइम है और ये स्ट्रेस है. सो दिस इज कॉल्ड द कंप्लीटली रिवर्सिबल स्ट्रेस. नाउ द रिपीटेड स्ट्रेस मीन्स द स्ट्रेस चेंज इट्स मैग्नीट्यूड रिपीटेडली, इट्स डायरेक्शन रिपीटेडली, बोल सकते हैं इसको भी, ये रिपीट करेगा. बट हियर the minimum stress, always remember sigma minimum stress must always be equal to 0, that is called the repeated stress, that is called the repeated stress. So अगर repeated stress को हम यहाँ draw करना चाहते हैं, repeated stress को draw करना चाहते हैं stress time diagram पे, तो वो कुछ इस तरीके से draw करेंगे. This is sigma stress, this is time. सो हम यहाँ से लिए इसे, ये कुछ मैग्नीट्यूड के साथ भी स्टार्ट हो सकता है, इट डिपेंड्स ऑन, एंड इट गोज एंड अगेन इट विल कंटिन्यू. सो दिस इज रिपीटेड स्ट्रेस. मिनिमम स्ट्रेस इज 0 एंड मैक्सिमम इज हैविंग सम वैल्यू, वेयर एज इन कंप्लीट रिवर्सिबल स्ट्रेस मैक्सिमम उतना ही था और अपोजिट नेचर, मैक्सिमम टेंशन में प्लस सिग्मा और कंप्रेशन में माइनस सिग्मा, डायरेक्शन चेंज होगी. And variable, it may have any kind. This, if I convert this, this is called the variable load. It may go in the negative side also. So अगर variable की बात करूँ तो उसे represent करने के लिए हमें maybe wrinkles, this is variable, this is sigma t, maybe sigma t, it may be like this, it may be like this, it may be it may be having nature like it is having some value like this. It is not equal to 0. It is not equal to 0. This is variable stress. So these are the three types. ये तीन तरीके के stresses हैं जो डायनेमिक लोड के अगेंस्ट डिज़ाइन करते हुए हम कंसिडर करते हैं. अगला, दिस इज कंप्लीटली रिवर्सिबल स्ट्रेस, हम पहले बात कर चुके हैं. ये किसी भी तरफ ये मैक्सिमम गया, दिस इज कॉल्ड सिग्मा ए, और इसे बोलते हैं हम एम्पलीट्यूड स्ट्रेस. एम्पलीट्यूड स्ट्रेस किसी भी तरफ, दिस इज एम्पलीट्यूड स्ट्रेस. Some authors use a symbol sigma v, and this sigma a is equals to sigma max minus sigma minimum divided by 2. यहाँ पे आप देख लें तो सिग्मा ए की वैल्यू कितनी होगी, सिग्मा मैक्स कितना है, sigma max is equals to plus, मैं कहूँ this is plus sigma, the value is plus sigma, and here the value is minus sigma. So, sigma max is equals to plus sigma minus minus sigma divided by 2, this is sigma, sigma amplitude, this is sigma a I am calculating. Sigma a is equals to plus sigma minus minus sigma upon 2, that is sigma amplitude is equals to sigma, sigma max को लिखा मैंने plus sigma और sigma minimum को लिखा minus sigma. You will get sigma amplitude is this. Now, one is the mean stress, another term we use a mean stress. So, what is mean stress? तो हम याद रखेंगे एम्पलीट्यूड स्ट्रेस कितनी है इसमें, सिग्मा, कंप्लीट रिवर्सिबल स्ट्रेस में सिग्मा. अब मीन स्ट्रेस की बात करें, सिग्मा एम इज इक्वल्स टू सिग्मा मैक्स प्लस सिग्मा मिनिमम divided by 2, and this definition will be applicable to all three types of the stresses. तीनों तरह में ये सिग्मा एम्पलीट्यूड के लिए, मीन स्ट्रेस के लिए ये डेफिनेशन लागू होगी. सिग्मा मैक्स कितना लिया था हमने, प्लस सिग्मा, सिग्मा मिनिमम कितना लिया था, माइनस सिग्मा. सो सिग्मा मीन कितना हो गया, सिग्मा प्लस प्लस माइनस सिग्मा बाई 2 इज इक्वल्स टू 0. दिस इज the mean stress. This is the mean stress, and third is range, that is stress range. So, stress range maximum से minimum के बीच में जितना difference है that is called range. So, यहाँ पे कितना range हो जाएगा, this is plus 2 times of sigma, plus 2 times of sigma. So, in this way we will calculate amplitude stress, mean stress and stress range, and these are the quantities which are of our interest during the design against dynamic load. This is repeated stress, I have already discussed. मैं पहले बता चुका हूँ कि अगर minimum stress 0 हो तो ये repeated stress हो जाएगी. यहाँ पे amplitude stress देखें, sigma a, so sigma max minus sigma minimum divided by 2. sigma max कितना, according to this curve this is plus sigma, sigma minimum कितना 0 और sigma a कितना, sigma by 2. यानी कि अगर मैं completely reversible stress को compare करूं repeated stress से तो amplitude stress का magnitude आधा हो जाता है कंप्लीट रिवर्सिबल स्ट्रेस से. सो यहाँ से भी ये पता चलेगा कि कंप्लीट रिवर्सिबल स्ट्रेस रिपीटेड स्ट्रेस से ज़्यादा डेंजरस है, ज़्यादा जो है डिस्ट्रक्शन क्रिएट कर सकती है. सिग्मा मीन की बात करें, सिग्मा एम, सो दैट इज सिग्मा मैक्स प्लस सिग्मा मिनिमम डिवाइडेड बाई 2. So, sigma plus 0 divided by 2, this is equal to sigma by 2. Mean stress भी sigma by 2 के बराबर है. रेंज की बात करें, sigma max minus sigma minimum. So, this is equal to sigma minus 0, that is sigma. So, this is range, or this is the mean stress, that is sigma mean, that is sigma by 2. इसके दोनों तरफ ये सिग्मा एम्पलीट्यूड, ये रिपीटेड स्ट्रेस में है. देन दिस इज वेरिएबल स्ट्रेस, यू कैन यूज द सेम, इसमें सिग्मा मीन और सिग्मा एम्पलीट्यूड स्ट्रेस की वैल्यू टाइम के अकॉर्डिंग डिफाइन करनी पड़ेगी. देन द व्हाट इज फैटिग, सो फैटिग का लिटरली मीनिंग होता थकान. So, if any material is not able to take up load further, then it is termed the material is termed as it is under fatigue, and the fatigue failure is very interesting. अभी तक हम ये समझते थे कि SYT के आगे जाके और SUT से आगे जाके मटेरियल फेल होता है, लेकिन इन फैटिग फेलियर अगर कोई मटेरियल कंप्लीटली रिवर्सिबल स्ट्रेस के तहत काम कर रहा हो तो इफ इट फेल्स, इट मे फेल in 90% cases even below the yield point, and without any warning, that kind of failure is called the fatigue failure. So, when the material is subjected to fluctuating stresses or fatigue stress, so यहाँ पे ये जरूर रखें आप, fatigue stress is completely reversible stress, completely reversible stress. ये completely reversible stress, तो material phase below the ultimate point, and in the case of completely reversible stress in more than 90% of cases below the yield point without any warning, this is called the fatigue failure. Then the fatigue failure mechanism, if we discuss, this is there, I have written already. So, fatigue failure mechanism, it constitute in two steps. It can be explained in two steps. First step is initiation of crack and then propagation of crack. Crack initiation and crack propagation will result in the reduction in the cross section or area, and F upon A. If A is reduced, then the magnitude of stress increases without any warning. So, I will discuss the mechanism as well as the ascent diagram to determine the endurance limit in the next lecture. So, for today